(0401) on the UK time. Biomimicry. Right.
why he thought. It was so beautifully done. It was so architectural. It was so precise. But it occurred to me, how in his small life had he already believed the myth that if something was that well done, that we must have done it? How did he not know? It's what we've all forgotten, that we're not the first ones to build. We're not the first ones to process cellulose. We're not the first ones to make paper. We're not the first ones to try to optimize packing space or to waterproof or to try to heat and cool a structure. We're not the first ones to build houses for our young. What's happening now in this field called biomimicry is that people are beginning to remember other organisms, the rest of the natural world, are doing things very similar to what we need to do. But in fact, they're doing them in a way that have allowed them to live gracefully on this planet for billions of years. So these people, biomimics, are nature's apprentices, and they're focusing on function. And what I'd like to do is show you a few of the things that they're learning. They have asked themselves, what if every time I started to invent something, I asked how would nature solve this? And here's what they're learning. This is an amazing picture from a Czech photographer named Jack Headley. This is a story about an engineer at J.R. West. They're the people who make the bullet train. It was called the bullet train because it was rounded in front, but every time it went into a tunnel, it would build up a pressure wave, and then it would create like a sonic boom when it exited. So the engineer's boss said, find a way to quiet this train. He happened to be a birder. He went to the equivalent of an Audubon Society meeting, and he studied, there was a film about kingfishers, and he thought to himself, they go from one density of medium, the air, into another density of medium, water, without a splash. Look at this picture, without a splash, so that they can see the fish. And he thought, what if we do this? Quieted the train, made it go 10% faster on 15% less electricity. How does nature repel bacteria? We're not the first ones to have to protect ourselves from some bacteria. Turns out that this is a Galapagos shark. It has no bacteria on its surface, no fouling on its surface, no barnacles. And it's not because it goes fast. It actually basks. It's a slow-moving shark. So how does it keep its body free of bacteria buildup? It doesn't do it with a chemical. It does it, turns out, with the same dentisoles that you had, on Speedo bathing suits that broke all those records in the Olympics. But it's a particular kind of pattern. And that pattern, the architecture of that pattern on its skin dentisoles, keep bacteria from being able to land and adhere. There's a company called Sharklet Technologies that's now putting this on the surfaces in hospitals to keep bacteria from landing, which is better than dousing it with antibacterials or harsh cleansers that many organisms are now becoming drug resistant. Hospital-acquired infections are now killing more people every year in the United States than die from AIDS or cancer or car accidents combined, about 100,000. This is a little critter that's in the Namibian desert, has no fresh water that it's able to drink, but it drinks water out of fog. It's got bumps on the back of its wing covers, and those bumps act like a magnet for water. They have water-loving tips and waxy sides. And the fog comes in and it builds up on the tips, and then it goes down the sides and into the critter's mouth. There's actually a scientist here at Oxford who studied this, Andrew Parker. And now kinetic and architectural firms like Grimshaw are starting to look at this as a way of coating buildings so that they gather water from fog. 10 times better than our fog-catching nets. CO2 as a building block. Organisms don't think of CO2 as a poison. Plants and organisms that make shells, coral, think of it as a building block. There's now a cement manufacturing company starting in the United States called Calera. They've borrowed the recipe from the coral reef, and they're using CO2 as a building block in cement, in concrete. Instead of cement usually emits a ton of CO2 for every ton of cement, now it's reversing that equation and actually sequestering half a ton of CO2, thanks to the recipe from the coral. None of these are using the organisms. They're really only using the blueprints or the recipes from the organisms. How does nature gather the sun's energy? This is a new kind of solar cell that's based on how a leaf works. It's self-assembling. It can be put down on any substrate whatsoever. It's extremely inexpensive and rechargeable every 5 years. It's actually a company that I'm involved in called OneSun with Paul Hawken. There are many ways that nature filters water, that takes salt out of water. We take water and we push it against a membrane, and then we wonder why the membrane clogs and why it takes so much electricity. Nature does something much more elegant, and it's in every cell. Every red blood cell of your body right now has these hourglass-shaped pores called aquaporins. They actually escort water molecules through. It's kind of a forward osmosis. They escort water molecules through and leave solutes on the other side. A company called Aquaporin is starting to make desalination membranes mimicking this technology. Trees and bones are constantly reforming themselves along lines of stress. This algorithm's been put into a software program that's now being used to make bridges lightweight, to make building beams lightweight. Actually, GM Opel used it to create that skeleton you see in what's called their bionic car. It lightweighted that skeleton using the minimum amount of material as an organism must for the maximum amount of strength. This beetle, unlike this chip bag here, this beetle uses one material, chitin, and it finds many, many ways to put many functions into it. It's waterproof. It's strong and resilient. It's breathable. It creates color through structure. Whereas that chip bag has about 7 layers to do all of those things. One of our major inventions that we need to be able to do to come even close to what these organisms can do is to find a way to minimize the amount of material, the kind of material we use, and to add design to it. We use 5 polymers in the natural world to do everything that you see. In our world, we use about 350 polymers to make all this. Nature is nano. Nanotechnology, nanoparticles, you hear a lot of worry about this, loose nanoparticles. What is really interesting to me is that not many people have been asking, how can we consult nature about how to make nanotechnology safe? Nature's been doing that for a long time, embedding nanoparticles in a material, for instance, always. In fact, sulfur-reducing bacteria, as part of their synthesis, they will emit, as a byproduct, nanoparticles into the water. But then right after that, they emit a protein that actually gathers and aggregates those nanoparticles so that they fall out of solution. Energy use. Organisms sip energy because they have to work or barter for every single bit that they get. And one of the largest fields right now in the world of energy grids, you hear about the smart grid. One of the largest consultants are the social insects, swarm technology. There's a company called Regen. They're looking at how ants and bees find their food and their flowers in the most effective way as a whole hive. And they're having appliances in your home talk to one another through that algorithm and determine how to minimize peak power use. There's a group of scientists in Cornell that are making what they call a synthetic tree because they're saying, there's no pump at the bottom of a tree.
Prada See Beyond Partnership.
That it's able to drink, but it drinks water out of fog. It's got bumps on the back of its wing covers, and those bumps act like a magnet for water. They have water-loving tips and waxy sides. And the fog comes in and it builds up on the tips, and then it goes down the sides and into the critter's mouth. There's actually a scientist here at Oxford who studied this, Andrew Parker. And now kinetic and architectural firms like Grimshaw are starting to look at this as a way of coating buildings so that they gather water from fog. 10 times better than our fog catching nets. CO2 as a building block. Organisms don't think of CO2 as a poison. Plants and organisms that make shells, coral, think of it as a building block. There's now a cement manufacturing company starting in the United States called Calera. They've borrowed the recipe from the coral reef, and they're using CO2 as a building block in cement, in concrete. Instead of cement usually emits a ton of CO2 for every ton of cement, now it's reversing that equation and actually sequestering half a ton of CO2, thanks to the recipe from the coral. None of these are using the organisms. They're really only using the blueprints or the recipes from the organisms. How does nature gather the sun's energy? This is a new kind of solar cell that's based on how a leaf works. It's self-assembling. It can be put down on any substrate whatsoever. It's extremely inexpensive and rechargeable every 5 years. It's actually a company that I'm involved in called OneSun with Paul Hawken. There are many, many ways that nature filters water, that takes salt out of water. We take water and we push it against a membrane, and then we wonder why the membrane clogs and why it takes so much electricity. Nature does something much more elegant, and it's in every cell. Every red blood cell of your body right now has these hourglass-shaped pores called aquaporins. They actually escort water molecules through. It's kind of a forward osmosis. They escort water molecules through and leave solutes on the other side. A company called Aquaporin is starting to make desalination membranes mimicking this technology. Trees and bones are constantly reforming themselves along lines of stress. This algorithm's been put into a software program that's now being used to make bridges lightweight, to make building beams lightweight. Actually, GM Opel used it to create that that skeleton you see in what's called their bionic car. It lightweighted that skeleton using the minimum amount of material as an organism must for the maximum amount of strength. This beetle, unlike this chip bag here, this beetle uses one material, chitin, and it finds many, many ways to put many functions into it. It's waterproof. It's strong and resilient. It's breathable. It creates color through structure. Whereas that chip bag has about 7 layers to do all of those things. One of our major inventions that we need to be able to do to come even close to what these organisms can do is to find a way to minimize the amount of material, the kind of material we use, and to add design to it. We use 5 polymers in the natural world to do everything that you see. In our world, we use about 350 polymers to make all this. Nature is nano. Nanotechnology, nanoparticles, you hear a lot of worry about this, loose nanoparticles. What is really interesting to me is that not many people have been asking, how can we consult nature about how to make nanotechnology safe? Nature's been doing that for a long time, embedding nanoparticles in a material, for instance, always. In fact, sulfur-reducing bacteria, as part of their synthesis, they will emit, as a byproduct, nanoparticles into the water. But then right after that, they emit a protein that actually gathers and aggregates those nanoparticles so that they fall out of solution. Energy use. Organisms sip energy because they have to work or barter for every single bit that they get. And one of the largest fields right now in the world of energy grids, you hear about the smart grid. One of the largest consultants are the social insects, swarm technology. There's a company called Regen. They're looking at how ants and bees find their food and their flowers in the most effective way as a whole hive. And they're having appliances in your home talk to one another through that algorithm and determine how to minimize peak power use. There's a group of scientists in Cornell that are making what they call a synthetic tree because they're saying, there's no pump at the bottom of a tree. It's capillary action and transpiration pulls water up a drop at a time, releasing it from a leaf and pulling it up through the roots. And they're creating, you can think of it as a kind of wallpaper. They're thinking about putting it on the insides of buildings to move water up without pumps. Amazon electric eel, incredibly endangered some of these species, creates 600 volts of electricity with the chemicals that are in your body. Even more interesting to me is that 600 volts doesn't fry it. We use PVC and we sheathe wires with PVC for insulation. These organisms, how are they insulating against their own electric charge? These are some questions that we've yet to ask. Here's a wind turbine manufacturer that went to a whale. Humpback whale has scalloped edges on its flippers, and those scalloped edges play with flow in such a way that it reduces drag by 32%. These wind turbines can rotate in incredibly slow wind speeds as a result. MIT just has a new radio chip that uses far less power than our chips, and it's based on the cochlear of your ear, able to pick up internet, wireless, television signals, and radio signals in the same chip. Finally, on an ecosystem scale, at Biomimicry Guild, which is my consulting company, we work with HOK architects. We're looking at building whole cities in their planning department. And what we're saying is that shouldn't our cities do at least as well in terms of ecosystem services as the native systems that they replace? So we're creating something called ecological performance standards that hold cities to this higher bar. The question is, biomimicry is an incredibly powerful way to innovate. The question I would ask is, what's worth solving? If you haven't seen this, it's pretty amazing. Dr. Adam Neiman. This is a depiction of all the water on Earth in relation to the volume of the Earth. All the ice, all the fresh water, all the seawater, and all the atmosphere that we can breathe in relation to the volume of the Earth. And inside those balls, life over 3.8 billion years has made a lush, livable place for us. And we are in a long, long line of organisms to come to this planet and ask ourselves, how can we live here gracefully over the long haul? How can we do what life has learned to do, which is to create conditions conducive to life? Now, in order to do this, the design challenge of our century, I think, we need a way to remind ourselves of those geniuses and to somehow meet them again. One of the big ideas, one of the big projects I've been honored to work on is a new website, and I would encourage you all to please go to it. It's called asknature.org. And what we're trying to do in a TED-esque way is to organize all biological information by design and engineering function. And we're working with EOL, Encyclopedia of Life, Ed Wilson's TED Wish, and he's gathering all biological information on one website. And the scientists who are contributing to EOL are answering a question: what can we learn from this organism? And that information will go into asknature.org. And hopefully, any inventor anywhere in the world will be able, in the moment of creation, to type in, how does nature remove salt from water? And up will come mangroves and sea turtles and your own kidneys. And we'll begin to be able to do as Cody does and actually be in touch with these incredible models, these elders that have been here far, far longer than we have. And hopefully with their help, we'll learn how to live on this earth and on this home that is ours, but not ours alone. Thank you very much.
That was audio from TED, and it was Biomimicry in Action, Janine Banyus.
I think when you spend time in nature,
concrete slabs and brick. Just like the soil inside a termite mound, these materials have a high... So that left Pierce with a seemingly impossible challenge. How do you design a building that cools itself? This is a termite mound. Millions of termites live inside these structures, some of which stretch an astonishing 30 feet high. Although these termite skyscrapers may look solid from the outside, they are actually covered in tiny holes that allow air to pass through freely. Like a giant lung, the structure inhales and exhales as temperatures rise and fall throughout the day. This termite ventilation inspired Pierce to use an approach known as biomimicry, imitating the ingenuity found in nature to solve human problems. Meet the Eastgate Center. The building is made from concrete slabs and brick. Just like the soil inside a termite mound, these materials have a high thermal mass, which means they can absorb a lot of heat without really changing temperature. The exterior of the building is prickly, like a cactus. By increasing the amount of surface area, heat loss is improved at night while heat gain is reduced during the day. Inside the building, low-power fans pull in cool night air from outside and disperse it throughout the 7 floors. The concrete blocks absorb the cold, insulating the building and chilling the circulating air. When the morning comes and temperatures rise, warm air is vented up through the ceiling and released by the chimneys. Thanks to this innovative design, temperatures inside stay at a comfortable 82 degrees during the day and 57 degrees at night. Not to mention, it uses up to 35% less energy than similar buildings in Zimbabwe. Since opening its doors in 1996, Mick Pierce's 90% natural climate control system has made the Eastgate Center a global landmark for sustainability. So, we must ask ourselves, if an architect could design a self-cooling building with termite-inspired climate control, what other innovations can Mother Nature inspire if we just paid closer attention?
try to keep you on earth. All right, so let's make a language test. Question for you. How many of you believe this photo was taken outside the building? Hands up.
Oh.
Of course, you're perfectly wrong. I mean, you are not wrong. You are the perfect audience to talk about biomimetics, as this concept involves a set of innovative technological solutions developed on the basis of natural systems observations. So today, I want to show you what we can learn from nature, how we can learn from nature, and how we can apply this knowledge into contemporary architectural design, which is, of course, closest to my heart. So, in contemporary architecture, biomimetics is one of the most actual phenomena. I believe the popularity of this topic may be attributed to the development of close links between biological sciences and innovative technologies. So, of course, it didn't start yesterday. In Art Nouveau, already at the end of 19th century, architects started to look at nature as the best source of inspiration. And that was later developed in so-called organic architecture in 20th century, where engineers used to observe natural structural systems like trees and used to apply these observations into their building and structures. Oh, spiderweb, the one I hate, but that's very popular tensile structure existing in nature, which was an inspiration for the pretty famous Olympic Stadium in Munich. So what has really changed? Why we speak about biomimetics today? First of all, we developed a more holistic approach. We look at the whole systems. And secondly, we started to change our attitudes towards environment, climate, sustainability. All right, so what does it really mean, biomimetics? The term was first used in 1969 by Otto Schmidt in the context of opportunities arising from applying the knowledge from the field of biology in medical engineering. And since then, biomimetics has been a fast developing tendency that provides an information transfer from biology to technical disciplines with purpose to understand natural systems and processes and to implement them in concepts and structures designed by humans. When we think today about biomimetic design, about biomimetic building, first we carry out so-called natural systems behavior analysis. If that sounds a little bit complicated, let me make this simple. We look at exchange mechanisms between external and internal environments. And now, those of you who listen carefully may want to stop me with a question. But is it ever possible to compare something that's so different? Biological systems, living organisms, and building that is obviously not alive. So can we say that the buildings breathe, consume, digest? Even worse, can they reproduce themselves? I see your faces. Some of you look a little bit nervous right now. No worries, I promise. I'm not going to show any building pornography, any procreation systems of the buildings. But yes, in a sense, they can. They carry out a series of metabolic processes. And I will show this in a moment. But the main purpose of biomimetic design in architecture is to create completely new, complex solutions that are based on biological systems. Let me explain this with this example. You can see this biofiltration wall system, and except from pretty interesting architectural design, you can see green plants here. And these green plants make a part of biofiltration system. As they breathe, they produce oxygen, they absorb carbon dioxide and air pollution. So we can say that the plant's breathing mechanism is an example of biological process applied in the building. However, biological processes represent a huge variety of complexity. I hope you would agree that one can notice a small difference between complexity and intelligence of processes occurring in plants and in humans. Even though some politicians seem to represent a small exception from this rule, let's just believe it's a general idea that similar is not identical. So some further research is necessary. A simple copy of the biological system would not work correctly in architecture. So how do we analyze these systems? Let's take a look at multi-level research model of biomimetics in architecture that I developed. And it always starts with something very simple. Selection and observations of biological prototype. It can be something as simple as a leaf. What do we analyze? Structure, function, reaction for stimuli, physical chemical properties, relations with environment, anything that we believe may be important and inspiring. The only thing we need to remember is to look at it like we have never seen it before. As remember, we are trying to develop some new knowledge here. So from here, we can move to the second level, from the leaf to the whole branch. And when first all the solutions were analyzed individually, then we look at them at the system level. And again, there is a huge complexity of biological systems. So to simplify the model, I have selected 3 basic systems that are similar in nature and in building. And these are structure, metabolism, and skin. So we continue observations, we apply the research result in the built environment, and we do not stop here. We continue research and we try to improve the functioning of the building, hopefully for the benefits of the users, not just architects. And from here, we can move to the third level. As for complexity, it can be compared to the whole tree. At the third level, we look at passive, active, and hybrid solutions, and we test them for practical verification of the model. So we follow nature also in the process that's similar to evolution, as we try to select the good ideas and eliminate the concepts that do not work so well, at least currently. So this is how it looks as a model, from biological prototype through selected systems, structure, metabolism, and skin. And these particular solutions I would prefer to explain on existing architectural examples, like this building designed by Mario Puccinella in Beijing. And we will start with structure. So as you can see, some parts of the building can move. And this is because flexible systems can adapt their structure and shape to changing environmental conditions. This can happen on passive, active, or hybrid mode. And this is something similar to what living organisms can do. Like opening and closing depend on temperature, humidity, solar radiation. At a passive mode, you can see the example of the same building. That's just a schedule. And the building was designed for a particular angle of sun during the year. So you can see that in winter, with lower position of the sun, solar radiation comes directly on the facade to provide passive solar gain. Speaking English, it means to warm us when we are in the office. In summer, when we prefer to avoid overheating, with higher position of the sun, a part of radiation would be reflected from the shadowing devices, which simultaneously convert the solar energy to electricity, as this we have photovoltaic panels, and a part is absorbed by green plants and used in photosynthesis. It's an amazing building. I could spend a lot of time speaking about this, but I can't. But I would prefer to show you some active structures that can provide adequate reaction for the external stimulus. And a specific example, very promising for future technologies, are pneumatic structures, pneumatic systems, especially the ones based on membranes. Like Gore-Tex is an example of complex hybrid membrane, and the especially interesting membranes, they combine durability of synthetic membranes, they are strong, and selectivity of cell membranes, so they can breathe. Also, some advanced strategies for heating and lighting can be inspired by phototropism. I'm sure you know some phototropic or heliotropic plants, like sunflowers that follow sun during the day, and the same can happen to some elements of the building. This is often combined with adaptive building schemes and simulated metabolic processes. So here we are at the mysterious level of metabolism of the building. Let's see what do we deal with. First of all, there is a series of exchange mechanisms between the building and environment. Buildings exchange gas, so we can say that they breathe. Sometimes phototropism is involved and photosynthesis, and there is exchange of liquid, like water intake or elimination of too much humidity, so we can compare it to evapotranspiration. Plenty of processes related to energy, consumption, absorption, production, transformation, and waste management, because the buildings and the users produce waste. But it's important that in nature, nothing is really a waste. Anything can be important source for something or someone else. So we can say that basically biology operates on well-designed circular economy models. There is also a steering system that we can compare to our central nervous system. In case of the building, such a brain is called BMS, and building management system in the real time selects the most appropriate strategy related to energy, humidity thermoregulation. Also, hybrid thermoregulation can be inspired by heterothermic organisms. The ones they adjust the body temperature to external conditions. In Energy Efficiency Center in Würzburg that you can see here, it is possible with heat storage in phase change materials. And it is a fantastic materials that transform their state from solid to liquid, depending on the temperature outside and on our needs. Also, it is supported with heating and cooling with infrared radiation technology. You can see the system working here. And at the skin level, we have a series of controlled metabolic processes: radiation, convection, and evaporation. And these processes work very well in combination with green roofs and green facades. Some of those are inspired by traditional architecture, like from Scandinavia, and they are very good because they provide excellent insulation. They help us with humidity control, and they also produce oxygen, so that with higher partial pressure of oxygen, our cognitive processes should work actually really well. Oh, here. It's again about phototropism, because some advanced building skins can involve third generation of photovoltaic cells, like this one with Fresnel lens and polygonal photovoltaic cell, transparent cells that allow for harvesting of that part of energy which was not converted to electricity. But okay, now I believe it's time to show you the biomimetic design concept in Brit, Austria, which was Austrian Pavilion for Expo Milano 2015. And the building was so spectacular because it was a real hybrid of nature and technology. The building had a very simple wooden core, but inside of it, and that's the photo where the photo was taken, there was a copy of Austrian mountain forest with over 12,000 of green species that the plants would produce oxygen enough for 1,800 visitors per hour. So how was it possible that the natural system was so efficient? And this wasn't me. This was because natural processes, evapotranspiration and photosynthesis, were supported with active technologies powered with photovoltaic energy. And the ambience was absolutely amazing, because when you would enter the pavilion from the middle of very hot Italian summer, you felt like you went into the forest that was cold and humid, and of course you could see the technology which was exposed in a clearly visible way to explain how the system works. There were fans and fog nozzles and sprinklers, so the impression was so fantastic.
Claire thinks it's weird that Annie eats Walker's crisps in a sandwich. Annie doesn't think about Claire at all. Walker's, your little slice of joy.
Fantastic, even with the play of light between the trees. And of course, I'm not saying that this building was a prototype for mass production. No, we should look at it as at an experiment that proved that we have knowledge and technology to create biomimetic buildings that are safe for environment and comfortable for the users. But the real secret is the novel perception of the built environment, and this is related to shifting baselines regarding sustainability, climate, ecosystems. And this is why I'm showing children here, because you surely notice how natural children are with all kind of innovative technologies. Smartphone, laptop, just robots, name it. And the same should happen to their attitude towards nature, towards renewable energy. The sooner we start the education, the better chances that we will grow a real post-fossil generation. And also the role of the building in the future should evolve from sustainable or less harmful relation to something that we can call endosymbiotic living environment for humans, or biological architecture that uses the same concepts that biology. So next time, when you feel that the big city is not so sexy anymore, instead of your usual gun fishing, you can say, take a walk on the wild side. Or if you live in biomimetic building, you can just say, let's go home. And that's my message for today. Because learning from nature can be absolutely amazing. And I hope you will open your eyes and enjoy the experience. And let's keep nature reloaded. So thank you very much for being such a wonderful audience today.
so you're traveling to a really warm country. I'll say Muscat, Oman comes to mind. Okay, so you're traveling to a really warm country. I'll say Muscat, Oman comes to mind. And you're thinking what you're going to put on. T-shirts and shorts, surely. Or one of your friends thought, let's go in this instead. After all, it was lovely when we went skiing the last time in the Alps. Well, that exactly is ridiculous by definition. And that's why the ills of duplictecture is just around us. In fact, duplictecture as a word is a fusion of duplicate and architecture. And if you ask my opinion, a lot of buildings in hot, humid, developing countries have embraced this. You could say culturally, you could say by way of design, and the ills, partly, you could ask me, is contributing perhaps more to global warming in terms of building implications than any other factor, in my opinion, in that context. If I look at these buildings, or if we looked at them, you might perhaps say nothing wrong with them. I mean, they look similar. They have high glazing percentages. They look nice, and I agree, they look nice. Until perhaps I told you that the one on the left is Separato Towers in Lagos, Nigeria, while the one on the right, of course, we know that's London. The ones on the right, of course, are suitable for their climate. They're lovely, they're fantastic design. They let as much light and heat in as should be in a temperate condition. Let's just say in Lagos, you are creating vertical gas chambers and ovens with that concept. Because you are running temperatures 26, and that's not even factoring the heat index. In fact, you might argue that the heat load or the cooling load of these buildings, if you perhaps just strip them of their glazing, you might begin to cut them by percentages without doing any other thing. Okay, let's just say the one at the top is London and the one at the bottom is Lagos. Shall we agree? No, scrap that. It's actually the other way around. Now, you see, when you need a second look to differentiate between the architecture of a temperate climate and the architecture of a hot, humid climate, you are in trouble. Effectively, what you have is building adaptations that haven't quite worked. Lagos is not the only client that is doing this. If you ask me, I was saying to my wife, perhaps I might scramble these tags and get our 3-year-old Gracie to shake it up and try to place them wherever she wished. And there are only a very few things more random than that. And see whether Daddy can place them back without looking at the original file. The fact is, duplictecture is not just a Lagos problem. If you went from Cairo and traveled through the coastline, we're doing just a photo analysis with one of my colleagues, all the way to Cape Town, you see buildings that if we actually did that experiment, many would struggle to put them where they belong because they're similar. Yet, from Cairo down to Cape Town, you would have gone through several different climates and microclimates. For example, if we look at these two buildings, and again, there's nothing wrong with them looking similar just by looking at them. Well, the one on the left is Astana, Kazakhstan. The lowest temperatures recorded is, I think, minus 62. And Lagos, of course, is in the late 20s to 30s. The shape and the form for the Palace of Peace and Reconciliation as designed is perfect, allowing as much solar insolation, trapping as much heat, perfect for Astana. But let's just say in Lagos, while it snows in Astana, if I came in any day and told you that, hey, it snowed in Lagos, just know that Armageddon has happened and we're no longer here. Yet, they have such similarities. I was talking to a friend that maybe we should start asking, what would nature have done here? Maybe we should start asking a few more questions about why is it that temperate plants look different from tropical plants? Well, they will and they should. Because common sense is very common in that community. Perhaps not in other climes. You get where I'm going. Because if you find out that these plants in the temperate region, they're trying to keep heat in, while the ones in the tropic have so much heat, they have to spread out. In fact, if you look at the needle-like leaves of the pine, which we have here, and of course we have in Astana as well, they're trying to cluster together. They're trying to limit exposure. They're trying to keep in the heat in. And the ones that have even leaves, as we saw in the earlier slot, in this earlier shot, try to get rid of them at the coldest temperatures, all to survive. But then you look at the cocoyam leaf in Lagos saying, here we are, so much sunlight. We just have to, have a party while we shield our younger ones, and we need to provide room for evapotranspiration because there's so much heat and there's so much warmth that we need to get rid of them. Unfortunately, this hasn't quite influenced our architecture as much as it should. So while on the left-hand side, once again, you have the Astana skyline, the Civic Center complex in Lagos fits in quite nicely if you were to just put it across to the next skyline. It's just that while the people in Astana are wearing their coats at this time of the year to keep with the cold weather, the guys in Lagos, let's just say sometimes they take extreme steps to keep cool. When I was taking this shot, the gentleman who was helping me out, he had to step away from the chillers because you know what happens at the back of air conditioners, they're very warm. So essentially what you have is these vertical ovens soaking up the heat and then spreading it back into the streets. And everybody's doing that. And we're saying that perhaps if you got everybody to stop doing this, perhaps you might drop the average temperatures by a few cents. The copying of designs is not because of money, definitely not. Because, design cost is 5-10% at the most in terms of the overall project cost. Besides, you still have to localize and adapt them, get a project architect, etc. So it's not money. So what is it then? When I was taking this shot, I asked the guys at the old IMD building I showed earlier, I said, what happened if you turned up to work without your suits? If you dress in t-shirts and, if you dress appropriate for the climate? They said, we'll probably get sacked. If we turn up for the interview that way, we wouldn't get the job. So there's something of a status, cultural, international style that is causing this. We know that climate change is real. Well, most of us. And then, of course, we know that the implications perhaps for Lagos is quite damning when you consider that it's a coastal town as well and at risk. It's not just the economy, it's not just the environment. There's also the idea of fading cultures. Things, art, design, concept, vernacular heritage styles that, with all the tapestry of it wrapped into that developed over years being scrapped suddenly. So what's the solution? Well, fortunately, Janine and several people who are working on this area have told us that nature can be our model, our measure, and our mentor. So if we look at the tropical rainforest, we can learn so much from the emergent layer, the canopy layer, all the way to the forest floor, working together in a climate that actually works for everybody. In fact, when we tried a rainforesticity model, we were thinking of, how will buildings shade themselves, shade each other, some commensalism, some level of symbiosis. The street view was actually like walking again in the tropical rainforest, just like you're walking around amongst buildings, not trees. But you get where it's going in terms of the shading and the thermal comfort that it achieves. Fortunately, the IMD building has been remodeled, and frankly, I was really impressed when I saw the picture by the team that did it in the mold of what the rainforest would have done. We know that the project, the Eastgate Tower in Zimbabwe, saved a whole lot of money. Why? Because these guys taught them, the Mick Pierce's team, that there's a way you can actually ventilate by drawing in cold air from the base and letting the hot warm air go up to the top. And if you let the valves, the right measure, the right places, just like the ants will do in this termite mound, this building here could actually save, as they reported, over 35%, total energy savings in cooling. One of my students, and I think some of my students maybe in the audience, said, well, she's from Harare. She said, Anthony, I never knew that when we saw that building and the way it was really working, we really wondered, why isn't that the template for all buildings moving forward? How come we found a few others still copying duplicate textures? I said, well, if you find out the answer, come tell me, because I'm asking the same questions. For me, nature never ceases to amaze us. And that's Antelope Canyon, by the way. No columns, no beams. But then you have some of the most ingenious structural design just by the forces of wind and pressure. You have so many factors going on. The gecko tells us that adhesives don't need to be poisonous, don't need to be loaded with chemicals. The polar bear tells us that insulation can be by form and texture and by having a black body skin. The bullet train has been inspired by birds and several animals. You have countless things to copy from. Why copy from where you don't belong or where it doesn't fit? The Beatles tell us that forest fires shouldn't be a problem. We can smell it. Likewise, your fire detectors should. And several other inspirational things that nature can tell us, that we have no reason in any climate to go and copy from a different climate thinking that it will make sense. So, of course, anytime we're going on holidays in Muscat, definitely, like the guys who said, why don't we use what we use for skiing in the Alps? Well, don't do that because it's wrong. Thanks for listening.
That was Anthony Ogbukiri. That was TED at Manchester. The video before that was called Green Technologies for the Future.
Get £30 when you bet.
That was Barbara Widera. Oh no.
It was fast, really fast, like pushing 170 miles per hour fast. But every time it exited a tunnel, it was loud. The noise was coming from a variety of sources, but whenever a train sped into a tunnel, it pushed waves of atmospheric pressure through the other end. The air exited tunnels with a sonic boom that could be heard 400 meters away. In dense residential areas, that was a huge problem. So an engineering team was brought in to design a quieter, faster, and more efficient train. And they had one secret weapon. Eiji Nakatsu, the general manager of the technical development department, was a bird watcher. Different components of the redesigned bullet train were based on different birds. Owls inspired the pantograph. That's the rig that connects the train to the electric wires above. Nakatsu modeled the redesign after their feathers, reducing noise by using the same serrations and curvature that allow them to silently swoop down to catch prey. The Adelie penguin, whose smooth body allows it to swim and slide effortlessly, inspired the pantograph's supporting shaft, redesigned for lower wind resistance. And perhaps most notable of all was the kingfisher. The kingfisher is a bird that dives into water to catch its prey. The unique shape of its beak allows it to do that while barely making a splash. Nakatsu took that shape to the design table. The team shot bullets shaped like different train nose models down a pipe to measure pressure waves and dropped them into water to measure the splash size. The quietest nose design was the one modeled most closely after the kingfisher's beak. When the redesign debuted in 1997, it was 10% faster, used 15% less electricity, and stayed under the 70 decibel noise limit in residential areas. And it did all that with the wings of an owl, the belly of a penguin, and the nose of a kingfisher. There's a name for design like this. It's called biomimicry.
The people who design our world usually never take a biology class, believe it or not. So they're novices in how the world works.
Products is called biomimicry.
Some of the world's most famous inventors have used it in their designs. Take, for instance, Leonardo da Vinci.
The quintessential Renaissance man wasn't only an incredible engineer, he was also a keen observer. Throughout his notebooks are numerous observations about birds and their flight, culminating in his sketches for flying machines.
Although Da Vinci never made a heavier-than-air flyer, when the Wright brothers first flew in Kitty Hawk, they too said they were inspired by their observations of pigeons.
And while flight may have been biomimetics' crowning achievements, the practice has inspired the design of a wide range of products, from Velcro to cars.
Back in 2005, Daimler Chrysler unveiled their bionic car concept, a vehicle inspired by both the shape of a yellow boxfish and growth patterns of bone.
You see, while the yellow boxfish is an odd-looking critter, its body shape actually makes it cut through the water with minimal drag. So Chrysler's designers borrowed it.
But to really make a revolutionary vehicle, the bionic car's designers looked to natural bone to dictate the way the car's frame was structured.
Bone is pretty tough stuff, but it's not totally solid. Bone actually grows to directly meet the tensile load that it will bear, so it's no heavier than it has to be.
Applying this concept to the bionic car's frame reduced the vehicle's weight while also making it stronger in just the right places.
In the end, using biomimicry helped the bionic car achieve a 70-mile-per-gallon fuel economy, while also scooting from 0 to 60 in 8 seconds, all on a 140-horsepower engine.
Now, the bionic car is pretty cool, but nature doesn't just exist on the macro scale. Most of the time, it's so small you have to view it through a microscope.
So now designers are looking to bacteria and viruses to help design products on the nanoscale.
One massive discovery that has the potential to revolutionize entire fields of products are carbon nanotubes.
Inspired by naturally occurring carbon structures, manufactured carbon nanotubes are some of the strongest materials known to man.
Scientists have discovered that carbon nanotubes are extremely hard and good thermal conductors, and that they may have superconducting properties, making them a pretty versatile material.
With biomimetics leading designers to create even more complex products, robust design tools and huge processing power will be key to effective product development.
This episode is sponsored by PTC.
What are we having today then, lads?
Ham sandwiches.
Nice one up then.
You hit the target like those scientists do. We'll be in Europe.
Now any sub can be super. With Super Sub.
Reliance on human ingenuity. A number of scientists and engineers are learning design secrets that might be best for all our reliance on human ingenuity. A number of scientists and engineers are learning design secrets that might be best described as second nature. Faith Saley shows what we mean.
Blink, and you'll miss it.
The frog tongue is incredibly fast. It can reach accelerations up to 12 times the acceleration of gravity. To put that into perspective, astronauts going up into space experience 2 to 3 times the acceleration of gravity.
To catch a glimpse of a frog tongue in action, you have to be pretty sharp or determined, both of which might describe Alexis Noel, a bioengineer at Georgia Tech University.
So you can imagine these extreme accelerations that are happening to the insect as it's being yanked back into the mouth, and yet this adhesive on the tongue is still able to maintain grip.
Noelle's research into that sticky stuff, frog saliva, began when she stumbled across a video that had gone viral.
And I actually ran across this really funny video of this bullfrog trying to eat insects off of an iPhone screen. Of course, they're fake insects, and they're scrolling down the screen. We thought it was hilarious. And so we started asking these questions like, how is this frog tongue so fast and so sticky? Like, how does it catch these insects in the blink of an eye? Being a mechanical engineer and dabbling in fluid mechanics, I'm like, oh, this is a really interesting adhesive question.
Noelle hopes that understanding the mechanics of frog saliva could lead to the development of futuristic adhesives. And if that seems far-fetched, then welcome to the world of biomimicry, where scientists look to nature for innovations. The shape of Japan's bullet train, for instance, was inspired by the shape of a kingfisher's beak. These windmill blades were modeled after the fins of a humpback whale. But the most ubiquitous biologically inspired innovation of all might be in your closet. In 1941, Swiss engineer Georges de Mestral went for a hike in the Alps and noticed the way burrs adhered to his clothing. Today, the hook and loop fastening system most of us call Velcro is used in thousands of products.
It's actually a new way of inventing. And so chemists and designers and architects and engineers, when they have a problem, they ask what in nature has already solved this problem.
If there's one person to thank for the popularity of biomimicry, it would be Janine Benyus.
You know, the core idea is that life's been on Earth 3.8 billion years, and that's a lot of R&D.
Benyus popularized the term 2 decades ago in her book.
You know, NFL helmets are based on how the woodpecker's skull.
What?
Yeah, the woodpecker has a very particular skull, and
Just spend some time with her at her home in Montana, and you get the sense nature has taught her to see the world a little differently.
when I look at a tree, I think now that it's pretty amazing chemistry operation going on, right? Silently. Once you start thinking this way, you realize that nature is full of technologies. If you think of technologies as just tools for living.
But while the scientific field might be new, there's nothing new about being inspired by nature.
We need new ideas, you know.
But what you're saying is the newest ideas are the oldest ideas.
That's, you know.
And they've been there all along.
Exactly.
By one estimate, biologically inspired innovations could contribute $425 billion to the country's gross domestic product by 2030.
And you put porcupine quills in your face.
Yeah, as an example, I mean, what we like to do from time to time some self-experimentation and really get a sense for, you know, what it is that we're working with.
It was porcupine. Biologically inspired innovations could contribute $425 billion to the country's gross domestic product by 2030.
And you put porcupine quills in your face.
Yeah, as an example, I mean, what we like to do from time to time some self-experimentation and really get a sense for, you know, what it is that we're working with.
It was porcupine quills that pointed scientist Jeff Karp towards a new design for a medical staple.
So it was known at the time that quills have these backwards-facing barbs. When you tried to remove the quill, the barb catches on the tissue fibers and then kind of displays out to the side, so it's even grabbing even more. And that's where it gets its incredible gripping force. And so this gave us inspiration for a new staple.
At his lab in Boston's Brigham and Women's Hospital, Karp is creating new medical devices using some old technology. Very old technology. Slug slime was a starting point for a medical glue that works in wet environments.
This is incredibly strong. It's holding bone together.
The way jellyfish tentacles fan out to ensnare plankton inspired a filter to capture cancer cells in blood.
There's literally, you know, hundreds of millions of years of research and development that's happening all around us. And if a creature or a plant is not able to come up with a solution, then it becomes extinct. And so, in essence, we're surrounded by solutions, which I see as ideas for solving problems.
Can our bone together? The way jellyfish tentacles fan out to ensnare plankton inspired a filter to capture cancer cells in blood.
There's literally, you know, hundreds of millions of years of research and development that's happening all around us. And if a creature or a plant is not able to come up with a solution, then it becomes extinct. And
Scientists and engineers are constantly looking to the future, thinking of new inventions. But where do all their ideas come from? Sure, some scientists do have that eureka moment when a brilliant idea will just pop into their heads. But there is one place of inspiration that has an abundance of tried and tested technology. Nature. It surrounds us. Planet Earth has millions of species. Scientists and engineers are constantly looking to the future, thinking of new inventions. But where do all their ideas come from? Sure, some scientists do have that eureka moment when a brilliant idea will just pop into their heads. But there is one place of inspiration that has an abundance of tried and tested technology. Nature. It surrounds us. Planet Earth has millions of species of animals, insects, and a diverse selection of plants. But how are scientists learning from them?
They're looking at ways of interpreting the mechanisms into the man-made world or into technology, which basically means scientists imitating nature. We call this particular area of research biomimetics.
The word biomimetics was invented in the 1950s by Otto Schmidt. He'd been helping his elder brother do some biological demonstrations using electronics, and he thought, well, why shouldn't electronics learn from biology?
We can take inspiration from biological systems. Biomimetics can show us how to make materials and products using a lot less resource than we use currently.
One of the most successful bits of biomimetics, and one of the earliest ones, is Velcro, which is invented by George de Mestral, who was walking his dog through the woods one Sunday, and they went through a patch of burdock. The seeds stuck onto the dog's coat, and he found it very difficult to pull the hooks out of the fur. So he thought, well, this is a great way of joining two materials when you haven't got any glue or anything like that, and you don't want a permanent join.
Shark skin has a unique surface, enabling them to swim at speed. New swimwear mimicking this has been developed to help professional athletes break new records. Taking inspiration from birds has helped to improve wing design on planes. There's wind tunnels with turbines based on whale fins. Even a squid has been looked at because of its ability to change colour depending on its environment. The ultimate camouflage system. Because of its incredible strength, scientists are even looking at how spiders produce silk as an alternative to materials currently being used.
People have been trying to make spider silk for 3,000 years. We still haven't done it. The spider has obviously got some very good tricks, and it's not just the chemistry. Part of it is the way the thread is pulled out from the back end of the spider, and it comes out very thin the faster you pull it out. The nearest we've got so far is Kevlar, which is used in sails on boats.
System. Because of its incredible strength, scientists are even looking at how spiders produce silk as an alternative to materials currently being used.
People have been trying to make spider silk for 3,000 years. We still haven't done it. The spider has obviously got some very good tricks, and it's not just the chemistry. Part of it is the way the thread is pulled out from the back end of the spider, and it comes out very thin the faster you pull it out. The nearest we've got so far is Kevlar, which is used in sails on boats. We can do the chemistry, but we can't do the stick.
Today, biomimetics has exploded, with hundreds of research labs globally working on ways to interpret nature's biological mechanisms. And in these films, I'm going to be exploring behind the scenes and looking at the very latest inventions, some amazing